Electronegativity is an atom's attraction for a shared pair of electrons. So it's really the ability of an atom to attract electrons to itself. The element with the highest electronegativity is fluorine. It is assigned a value of 4.0. And so you'll notice the most electronegative elements are going to be up here in this corner. The least electronegative elements are going to be in the lower left. So what's the trend as you move across a period? As you move across a period, electronegativity is going to increase. And what happens as you move down a group? The electronegativity is going to decrease. And so basically, kind of a general rule of thumb, the closer an element is to fluorine, the more electronegative it is. Now that doesn't count for the noble gases. They generally do not have electronegativities. They don't have an attraction for electrons because they don't share pairs, because they already have their perfect octet. Out of the following pairs of elements, which one has similar physical and chemical properties? That's got to be B. Sodium, potassium, rubidium, cesium. Why? Those are all elements of the same family. Those are all alkali metals. They have the same valence, electron configuration, similar properties. Elements that have properties similar to calcium, it could be any of the following. It could be beryllium, could be magnesium, could be strontium, could be barium, could be radium. Why? All of those elements are members of the second group, which are the alkaline earth metals. They all have the same valence electron configuration. They all have two valence electrons traveling spherically. So similar properties. Okay, in order of increasing atomic size, the smallest is going to be oxygen. It is smaller than or less than sulfur, which is smaller than selenium, which is smaller than tellurium. So this is actually a group trend. As you go down a group, the radius gets larger. Why? More energy levels. Okay, out of the following pairs, rubidium is going to be larger. Why? Rubidium has 2 more energy levels than sodium. Let's see, strontium and calcium. Looks like it's going to be strontium. Why? Once again, strontium has an additional energy level than calcium. It's going to be bigger. Carbon and tin. That's going to be tin, largely for the same reason. Tin has, let's see, 3 more energy levels than carbon. And then sulfur and oxygen. Sulfur is larger. Why? It has 1 more energy level. Okay, the tendency to lose valence electrons. Lithium is going to tend to lose them before carbon. Why? Lithium only has 1, and it's much easier to get rid of 1 than it is to go look for 7 more. Carbon already had 4. Let's see, magnesium and barium. Okay, this time magnesium and barium have the same number of valence, but barium is going to be easier to lose 1. Why? They're further away from the nucleus. They're clear out in the 6th energy level. And then cesium and sodium, once again, it's going to be cesium, largely because they have the same number of valence. They both have 1, but cesiums are clear out in the 6th energy level compared to sodium, which they're in the 3rd energy level. The further away they are from the nucleus, the easier they are to lose. Okay, out of the following pairs, which one has the highest electronegativity value? Well, out of bromine and fluorine, fluorine's always, if fluorine's a choice, it's always going to be the most electronegative, because you'll notice it has the highest value at 4.0. Carbon and oxygen, once again, it's going to be oxygen. And one other thing you'll notice is that generally the closer an element is to fluorine, the more electronegative it's going to be. So now here's carbon, there's the oxygen. Oxygen is closer. Oxygen has the highest electronegativity. Out of fluorine and neon, it's got to be fluorine. Neon's not even listed on this table. Why? It's a noble gas. It doesn't have an attraction for any more electrons. And then bromine and calcium, it's definitely going to be bromine. Once again, it has 7 valence. It really wants to have 8. calcium only has 2. Okay, out of the following, which one is the most reactive? Strontium and calcium have the same number of valence, but strontium is going to be more reactive because it's going to more loosely hold on to its valence because they're way far out. Iodine and fluorine. Fluorine is going to be more reactive, even though they both have 7. Its attraction for additional electrons is going to be greater because they're so much closer to the nucleus. Selenium or oxygen. Oxygen for the same reason. They both have 2, they're missing 2 valence. They both have 6. Oxygen are going to be a lot closer to the nucleus. And then potassium or cesium. Cesium. It has 1, just like potassium, it's willing to give up. And because that valence electron is much further away, it has a less attraction for it, more reactive. Okay, strontium is a metal. Boron is going to be a metalloid. Phosphorus is going to be a nonmetal. And then arsenic is another metalloid. The main difference between an ionic bond and a covalent bond. An ionic bond, you have some element losing an electron and another element gaining that electron, and then they stick together due to opposite electrostatic charges. Covalent, just the word covalent means the valence electrons are together, they are shared. So covalent is sharing valence electrons. 2 examples of ionic compounds. Largely ionic compounds are going to be composed of a metal and a nonmetal. So anything where you have some metallic element bonded to a nonmetallic. So sodium chloride would be an example. It could even be something like a polyatomic. So there is, let's say it's iron 3 nitrate. So you have a cation and a polyatomic anion, still an ionic compound. 2 examples of covalent. Largely what you're going to see in covalent compounds is 2 nonmetals bound together. So examples of this, like carbon dioxide would be an example of a covalent compound. You could even have more, let's see, like C12, H22, O11. There's sucrose, all nonmetals that is covalently bonded together. Organic chemistry is really the chemistry of living things or things that were once living. Largely they contain carbon. Examples of organic compounds, here's an example. This would be methane, CH4, natural gas. Another example, let's do octane, one of the major components of gasoline. You don't have to be able to name these, just be able to recognize that they are indeed organic molecules. The major difference between polar and nonpolar covalent bonds, with nonpolar, it means they're sharing electrons equally. Anytime you have a diatomic molecule, like for example, like fluorine, okay, because the fluorine atoms are the exact same, the electrons shared will have no preference to one fluorine atom over the other. So there is equal sharing, so that would be an example of a nonpolar covalent bond. Polar, on the other end, means it has opposite ends, means their electronegativity difference is great enough that they share, but they do not share necessarily equally. An example of a polar covalent bond would be one between hydrogen and oxygen in water. Okay, they're sharing electrons, but their electronegativity difference is great enough that oxygen does not share equally. It takes more than its share of electrons. And so what happens is that you end up having a slightly negative end here and a slightly positive. Those are not S's, those are not 8's, those are lowercase deltas. That means slight or partial. And so because the electrons spend most of their time around oxygen, it has a negative charge, leaving just these protons out here on this end of the water molecule, giving them a slight positive charge. To do this activity, you would need to have an electronegativity table listed here, and you'd have to have some knowledge of this chart. So if the electronegativity difference is between 0 and 0.5,
Notice it's nonpolar covalent, which means they share equally. The electrons do not favor one of the atoms over the other. Their electronegativities are too similar. Anything with electronegativity difference between 0.5 and 2.0 is said to be polar, which means there are areas of positive and negative charge because there is unequal sharing. And then if you take the two elements that are bound together and you notice they have an electronegativity of greater than 2, it is said to be ionic. Okay, so that's gain and loss of electrons. If you don't have this table, there's a way you can kind of figure it out by just looking at the type of elements that are bonded together. If you look at sodium and sulfur, you have a metal and a nonmetal. Whenever you have metals and nonmetals, that's indicative of an ionic compound. Okay, hydrogen and oxygen, you'll notice on the table they're fairly far apart. They're both nonmetals, so that means that these form a polar covalent compound. Carbon and chlorine, their electronegativity falls kind of right on that borderline. But I would say it is a polar molecule because if you look at their differences, it's 0.5, so it's right in between. Polar is good enough. Lithium and bromine, you have a metal and a nonmetal. Once again, this is going to be an ionic compound. Iron and chlorine, once again, metal, nonmetal. This is going to be ionic. And then two hydrogens, this would be like a diatomic molecule. This would definitely be nonpolar. Why? The electrons that are shared between them do not favor one hydrogen atom over the other. They have the same electronegativity. They share equally, nonpolar. Anytime I see oxidation reduction reaction problems, I always think of the acronym oil rig. Okay, if I can just remember oil rig, I can remember what is oxidation, what is reduction. Oxidation is loss of electrons. Reduction is the gain of electrons. So oxidation is loss, reduction is gain, oil rig. So in reading this, as oxidation reactions involve a loss of electrons. So oxidation involves the, once again, loss. I don't know why it's on there twice, but the loss of reductions, whereas reduction involves the gain. So I'm not certain why it asked that twice, but there you have it. Alright, so in recalling from the last slide, oil rig, oxidation is lost, reduction is gain of electrons. I look at the first one, sodium. Sodium turning into a sodium cation and an electron. And so in order to become a positive ion, it must lose electrons. This is an oxidation. Here you have chlorine gaining electrons to become chloride anions. So this is a reduction. So B is a reduction. Aluminum, once again, you have aluminum ions gaining 3 electrons to form aluminum metal. This would be another reduction. And then here you have iron turning into iron 2 ions and 2 electrons, so the iron is losing electrons. This is an oxidation. Alright, time for some nomenclature review. Okay, you'll notice that silicon is a metalloid, so we're going to treat it as if it were a nonmetal, and 2 oxygen atoms, so this is silicon dioxide. Okay, when naming this compound, you'll notice that I have a transition metal that has various charges. And let's see, I have a polyatomic anion here. So the 1 goes up there, that is the charge of nitrate, so we're good. The 2 comes up here. So the charge of copper is 2+. That tells me this compound is copper 2 nitrate.